Hello everyone, welcome back. In this video we are going to learn about aggregation functions. So these are going to be things like the mean or the total sum over a Numpy array or the variance and so forth. So to start off we're going to begin by importing Numpy as NP. Looks like I already typed that before the start of the video. And then we're going to get a list of the numbers 0 through 9. To do this we do A is equal to np.arange 10. Take a look. We see we get the numbers 0 through 9. Now the first thing we're going to try to do is we're going to try to add up all of these numbers. I'm just going to make my screen a little bit smaller. And we can do this one of two ways. First is to go np.sum of A. And the other, perhaps simpler way, is just to go A.sum with parentheses. So one is using the sum function that is part of the NumPy module, whereas the other is using a method of a NumPy array, because we can essentially view NumPy arrays as like a class object, so they have their own methods. And so the story is the same with the min and the max. So we can do a.mean, np.mean, a, np.max, a.max, a.min, np.min. Now another thing we might want to do is to try to multiply all of the numbers together. So for this we're going to use the prod command. And so we could do a.prod. And before we press enter, let's think what we're going to get. We're multiplying all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. So you might think you're going to get 9 factorial, but there's also the 0, so we're actually going to get a 0. So we might want to avoid the 0 term, and so one way we could do this is we could take the subarray starting at entry index 1 through the rest, and then take the prod of that. And now we get 9 factorial, which is just when you multiply 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9. So in our next example, we're going to do something a little bit more statistical. And so we might want to look at the variance of a NumPy array. And so if your statistics is a little bit rusty, the variance of a set of numbers, what you do is you take the average, add them all up, divide by the number of numbers. Then you look at how much each term differs from the average. You square it, add all of those terms up, and then divide again by the number of numbers. So this looks like a complicated formula, but it actually is going to be a one-liner once we use our pre-designed functions. So we could say x is equal to np.random.rand. And then we could look at either x.var, or we could look at np.var of x. So that's the formula. I'm going to show you another way to do this to reinforce some concepts. But first I should mention that the way you should think of the variance is a measure of how spread out your data is. So x bar is like the average value, and x1 minus x bar is like how different it's like the variation from the middle number, from the mean. And so a big variance means that most of the numbers are far away from the variance, whereas if the variance was equal to 0, this would mean that every single point was the same. Okay, so now let's look at this formula again. So we have the average of the squares of the errors. So let's implement that using NumPy arrays. So to do this, we could say x minus x dot mean, and then we could square that, and then we could take the mean of that. And lo and behold, we again get the exact same number as before. So up next is Boolean aggregation. And this is where we're going to only want to sum over a subset of the data. This is going to become really useful in a couple of weeks when we start getting to panel data, pandas. So first what we're going to do is I'm going to set A back to being the A range. I'm going to create a mask, which is going to be only the entries which are greater than 7, and look at the entries which satisfy the mask. It's just the 8 and the 9 because those are the numbers where the condition that A greater than 7 is true. So now if we want to just sum over those, we could do np.sum of a mask, and we add up the two numbers which are there. We could also try to do a mask.sum, and that will work the same way. For these ones, though, where it's a little bit more complicated, I personally think that on these problems, using the function notation rather than the method notation is a bit more clear. Now, we can do the same thing with mean, mins, and max. I'm not going to write it out again. But the two other things which I'm going to mention is that there's the any and the alls. So any is going to be true if there's at least one entry for which it's true. So we do np.any mask, and we get true. And all is only going to be true if the mask is true for all of them. Oh, sorry, and type O. There we go. Yeah, so np.any mask will only return true if it's true for all of them. Okay, up next is aggregation against multiple dimensions. So for this, what we're going to do is we're going to create a 3x5 grid. So we first make a list of 15 numbers, and then we use np.reshape to make it 3x5. And this is probably going to be the trickiest part of the video. So if you've gotten so far, I encourage you to maybe pause the video, take 10 deep breaths. We don't have that much, there's not that much more. But this next part is going to be the tricky part. So make sure you pause, get some energy going, and now let's get after it. All right. Welcome back from your pause. So if we just do a.sum, we get what you get when you add up all of the entries in there. But sometimes you want to just add up along the rows or just add up along the columns. And so what we can do is we can say b is equal to sum.axis equals 0. Take a look at b. And here what we see is that we got 15, 18, and 21. So what we did is we went along each column. We get the sum of the numbers in column 0, sum of the numbers in column 1. 1 plus 6 plus 11 is 18. Sum over this column. And then we can do it the other way, where we could say C is equal to a.sum axis equals 1. And now here, we're going to get the sum of the sum of each row. So the hard part is remembering which is which. And so the way that there's a couple of ways you can remember this. So the key is that that axis 0 is the rows, axis 1 is the columns. And so the two ways to remember this is that when you say axis is equal to 0, that's the axis which gets eliminated. So we summed over axis equals 0, and so we're just left with axis equals 1, because that's the one that's eliminated. So when you sum over axis equals 0, you're just left with the 5 columns, but the 3 rows are collapsed. So I do think that this is actually going to be quite helpful to think about if we write this in matrix notation. So we can think of it as a matrix with indices I and j. And so when we have axis 0, this means we're going to sum over index 0, which is the I. So we do the sum over I, and so we just get something that depends on j. So we get bj is the sum over I of the aij's. It's axis 0, then that's the thing that we are computing, and that's the thing we're using to do the summation. And then the story is the same, but the other way around with C. So again, this is something which is really confusing for most people. It was confusing to me when I first learned it, but you'll get the hang of it with some practice. So we can also do similar things with min. So a dot min will give you the min of each column. You could do a dot max with axis equals to 1 to give you the max of each row. Or you could do a dot mean, axis equals to 1, and this will give you the max of each row. Sorry, the mean of each row. And if we want to get really wild, we could even do the cumulative sum. So we could do the sum up to that entry. And that'll give you the cumulative sum. So the last topic here is going to be dealing with nans. So nan stands for not a number. And the problem is that when you try to take the average of some things and there's one missing data point, you're going to get all sorts of problems. So what we're going to do is we're going to first convert a to float by multiplying by 1.0. And then we're going to set the first row to be nans, np.nan, and then a, where the float conversion is needed in order for the nans to work. And okay, so now let's try to take the means. So if we try to take the mean of each row, what we're going to get is the mean of each column. We're going to get nan. So this is because it's trying to take the average of 5, 100, and not a number. This doesn't make any sense, so it just returns not a number. And this is what's called nans propagating. Once you're doing a calculation where there's a nan involved, the nans will just propagate forward and everything will be a nan. Now, on the other hand, if we did a dot mean with axis equals to 1, here what we're going to see is that the first entry is going to be the average of all nans, so that doesn't make any sense. But the last two, they're all real numbers, so it actually is still able to take the mean. And so the last thing I want to mention is nan mean, because this situation is actually going to be really common when we start working with real data. Real data is collected by people. People make mistakes. Sometimes equipment malfunctions. And so you might have 3 pieces of information for a particular data point, but you might be missing another one, or somebody wrote something down wrong, or who knows. This comes all the way. You don't want to completely throw out your data set. So what you want to do is you want to take the mean of the valid entries. And so for this, you do np.nammean. A-axis is equal to 0. And this will then give you the means of the entries that are not nams. So 7.5 is the mean of the 5 and the 10. The 8.5 is the mean of the 6 and the 11. And when you use nam mean, it just ignores the nams. And so lastly, I'm going to conclude by mentioning that the story with nam sum, nam max, nam min, basically exactly the same. And that's it for this video. I will see you again next time.